Hi, my name is Brian Caffo, and this is Introduction to Regression. This class is co-taught by my co-instructors for the data science track, Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So let's talk about the kinds of questions that we're going to try to answer in this class. So the data that we're going to be looking at, in fact, let me go back to this previous page. There we go. The data we're going to be looking at is from this fellow right here, Francis Galton, who we'll talk a little bit about later, but he was a famous figure in statistics. And he developed the word and the concept regression. And what's interesting is that his data is still actually relevant. So one of the data sets that he used in developing regression was using parents' height to predict children's height. And in fact, there was this article not too long ago in the American Journal or the European Journal of Human Genetics that compared using genetic information to using Galton's Victorian era model, so I would suggest that you look at that paper. It's also a bit of a commentary on the utility of genetic information for predicting something as simple as height that's perceived at least to be mostly genetic. So at any rate, read that article, it's quite fun. But for our purposes, we're going to be talking not only about how can we use parents' height to predict children's height, so that's the example of one of the kinds of questions we'll answer, but we're going to have an entire class on prediction. And we're going to talk about modern prediction, high-dimensional predictors, complex interactions, very complex model spaces. So we'll actually talk a lot about prediction. So what I want to focus on this class is actually the second question, which is to find a parsimonious, easily described mean relationship between parents and children's heights. And what I mean by parsimonious is I mean sort of as simple as possible and no simpler, and interpretable. We want a simple, interpretable model to describe the relationship between parents' height and children's height. And that's what regression is really good at compared to, say, more modern machine learning algorithms. It gives you very interpretable models. We'll also talk about how do we quantify what we can't explain, residual variation. We'll talk about how we can take an alternate variable. Maybe we won't exactly do this example, but we'll talk about how we can use other variables and show how these other variables impact the utility of parents' height for predicting children's height and quantify the amount of variation explained by either. And we'll also figure out what assumptions are needed in order to try and generalize from not only the data that we have in hand, but to the population of parents and the population of children. And then there's this very interesting question, this very last question, which we'll have a lecture on just for fun, which is why is it that children of very tall parents, they tend to be tall, but a little bit shorter? So if you go to the NBA, which is the American National Basketball Association, and look at the players, look at their children. Their children tend to be tall, but not as tall as their parents, or even factoring the case that the spouse tends to be a lot shorter than the player, even factoring that in. And so why is that? Same thing is true for shorter parents. Their children tend to be short, but a little bit taller for very short parents. Seemingly paradoxically, why is it that parents of really tall children tend to be a little bit shorter? And why do parents of really short children tend to be a little bit taller? Okay, so that's this idea is regression to the mean, and we'll explore that because at first blush it seems a little bit counterintuitive. So let's actually look at this data by Francis Galton. It was collected in 1885. Galton was a statistician he invented the terms and concepts regression and correlation. He was a very brilliant person. He was also the cousin of Charles Darwin, and I think at the time being, A, both related to Darwin, and B, kind of at the time evolution was sort of discovered, it sort of influenced his thinking and kinds of problems that he worked on. He also founded the journal Biometrica. So anyway, he was a very interesting character. You should read up on him. He's just an interesting character in history. So let's look at his data that was formative in his coming up with the idea of regression. So the parents are all heterosexual couples. I think the measurements are all in inches. because women tend to be a little bit shorter than men, he needed a correction. You couldn't just average the parent's height. So he multiplied the female heights by 1.08. And so let's not stress too much over whether or not this is the right thing to do. He also has another data set where it's just fathers and sons, so that you get rid of the complexity of adding a second gender. But for the time being, let's just kind of sort of forget about this and just assume that his correction is about right. And then in this plot that the plots that we're going to overplotting it is an issue because of discretization, and we'll talk about how to handle that. So here we go. Let's start coding. So first thing we're going to do is do library right here, library using R. That's using R for introductory statistics is the name of the text that has this R package associated with it. We're going to get the data by doing data Galton. And I just put a semicolon here so that I didn't want a line break because I didn't have enough room for my plot. So if you want multiple commands on a single line in R, you have to put a semicolon between them, but if you put a new line each time, then you don't have to include that semicolon. mfrow here, this command right here, just simply says I want one row, two columns, fill my plots in that way. Okay, and then hist is histogram, and the $sign grabs that variable from my data frame. So Galton $child grabs the child variable, the Galton $parent grabs the parent variable. There's no missing data or any kind of complexities of that sort. Color blue, I want the color to be blue. Breaks tells me how many histogram breaks we'll have. Okay, and there's our two plots. The plots of the children and the parent seem fairly similar. I think the average height was about 5 feet 7 inches or so for both children and parents. So this is an interesting plot, but what we're really interested in, these are paired observations, so we've lost the pairing information when we looked at children by themselves and parents by themselves. But we'd like to, because all of these children, their specific parents are also indicated in the data set, so we'd like to do something like a scatter plot to investigate the joint relationship. But before we describe that joint relationship, let's just talk about summarizing the marginal. So when I say marginal, I mean the distribution of children disregarding parents and the distribution of parents disregarding children. That's what I mean by marginal. So let's just talk about summarizing the marginal information in each of these by themselves. And let's think about, is there a way that we could describe the middle of these data sets? So let's let yi be the height of child I, for in this case there's 928 of them, and define the middle as the value that minimizes this quantity right here. The sum of the squared distances between the data and this middle value, mu. And that turns out to be the actual center of mass of the histogram. And let me just describe what I mean by that. Is if these bars were all sort of weights, that weighed proportional to their height, right, and they were all the same width, and if we wanted to find the point where, if we were to put our finger there, right, if we were to put our finger at the point where this would balance out as if it was sort of, as if you were actually trying to do the physical experiment, that would be the physical center of mass of these collections of weights. And that's exactly what minimizing this least squares criteria right here gives us, the physical center of mass. From a statistical perspective, it makes a lot of sense. Well, why don't we define the middle as that point that minimizes the distance from all the points, right? Find the point that if we were to take the average distance between all the other points, squared distance in this case, the one that makes that the least, right? That seems like a reasonable place, and that's called least squares. Kind of for obvious reasons, right? All these guys are squared, and we're trying to find the minimum. And you might have guessed that the correct answer in this case works out to be the sample mean, the arithmetic mean, x bar. Where's that guy? Right there, x bar. Let's actually go through an experiment to show that it happens, and also this way I can show you the manipulate function in RStudio. So we're going to use RStudio's manipulate function to find the value of mu that minimizes the sum of the squared deviations. Okay, I wanted to go through this slide, but I actually wanted to execute the code. Just to remind you, all of the lecture notes in this class are on GitHub as part of our data science track, so it's all perfectly reproducible. And all the code for everything, whether it's included in the slide or not, is actually embedded in this file index.rmd. R stands for R Markdown. It's an R Markdown document. So here's like these three little slashes say to display the code. Let's actually illustrate. I'm going to use the manipulate function. So I'm going to do library manipulate, and then I created my own histogram function here, and there you go. You can go through the code, and basically all that does is create a histogram function to go into manipulate, and then the histogram function only depends on this one variable mu, which is where it puts the line where it's estimating the mean to be at. So here's my manipulate function. Now, so focus over here, okay? And here you can see the value of mu that it's currently at, and then that the mean squared error. In this case, I took the mean squared error. I took the average squared error rather than the sum of the squared errors. But obviously, if you minimize the mean squared error, you minimize the sum of the squared errors. So okay, so now we can move this slider along and see how, as we change our mean here in this case to 64.5, how we decrease the mean squared error. And what we want to do is find the point where we can put this red line that minimizes the sum of the squared errors, or the mean squared error in this case, what I'm displaying. And as you can see, you know, it's going to be somewhere right around here, right? Let's see. Oh, it looks like right there. It looks like around 68. Or so, but let's actually figure out what it is. Of course, you can always just do mean Galton star child, and I'll give it to you exactly. It's 68.08. But anyway, this just shows you what least squares is doing. It's sort of moving around that red line and finding the exact optimal place that will balance out this histogram as if you were putting your finger underneath it. Okay, so just to remind us, the least squares mean works out to be the empirical mean. Here I show you exactly where it is and how you can just draw where the mean is on the histogram itself. And then let's actually just go through the math as to prove that the least squares mean has to be the empirical mean. We don't just have to do it with, or we don't have to just do it experimentally by using manipulate. We can actually figure this out. So let's start with our least squares mean criteria. And again, if you want to skip some of these details, I'm providing them just for the people that are interested. If you want to take the class where you skip over a lot of these kind of intricate mathematical equations, then don't worry about it. That's perfectly fine. The quiz questions won't focus on the mathematics. But if you're interested in the mathematics, I do all the mathematics in such a way that you don't require either calculus or linear algebra. So all you need to know is basically how you can, if you can do a little bit of symbolic algebra and summation notation, you should be fine. Okay, here's the least squares criteria. Let's add and subtract y bar, okay? And then let's go to this next line. If we were to take this guy and square it out, we'd wind up with yi minus y bar squared part. We'd wind up with a 2 times this cross product part, and then we'd end up with a y bar minus mu part. Okay, this part right here, right, the y bar minus mu part doesn't depend on I, so we can pull it out of the sum to right there. And if we move this sum inside the parentheses, right, y bar doesn't depend on I, so it works out to be ny bar if we add it up n times, and we have summation yi. Okay, so summation yi, just remember we define y bar as summation I equal 1 to n yi over n. So of course summation yi is equal to ny bar, so this whole thing is 0. Get rid of that. And then you wind up with this guy right here, plus this extra term right here. But notice all of these terms are positive because they're a bunch of squared things. So we're adding up a bunch of squared things, so it's positive. So, right, so if we get rid of it, we can only get smaller, right? If we have a number and we take away a positive thing, then it can only get smaller. So we create that we have to get smaller when we get rid of that, and we get this guy. So okay, so just to recap, for any arbitrary mu, the least squares criteria, the least squares equation, is larger than if we plug in mu equal y bar. So that must mean y bar minimizes that equation. So it's interesting that you can show this very easily without any calculus or anything like that. Okay, so let's look at Galton's actual data, comparing children's heights and their parents' heights. So you can just do plot if you want to. It's right here. You do get a lot of these points in here. A lot of these points are overplotted. They represent several points. What I do here is I actually have the size of the point be the number of points at that particular child-parent combination. And the code is in the Markdown document, so you can do it. It's several lines of code, but it's nothing terribly difficult. So that's very useful. So what we'd like is to kind of, what we're going to talk about is how do we fit some sort of regression. Oops, not what I want. How do we fit the best line through this guy? How do we fit a best line where the lines, how the line is fit is impacted by, how many data points we have at each particular combination. To start out with, why don't we forget about the best line in general? Why don't we do the following? Let's imagine I have some data, some XY data. Here's my Y, and here's my X. And I'm going to put a pivot here at the origin at the point 0, 0. And then I want to just move this line in up or down relative to this angle right here, right? In a way that minimizes the distances between the points and the line, right? Now, the reason I'm tying it down at the origin is just because then I only have one parameter to think about how I move that line in terms of its angle. And this one obviously wouldn't be that good, so we'd want maybe this one would do a little bit better. Okay, so the way we do that, we can actually just go back to our least squares criteria. So a line through the origin is y equal x beta, right? That's a line through the origin. It has an intercept set to 0. So if our xi and yi are our individual points, and we fit the line y equal x beta, then this criteria right there minimizes the sum of the vertical distances between the y points and the line, right? So if this is our line, and we plug in xi, then the fitted value at that particular xi is yi hat, which is equal to xi beta. The distance between yi and yi hat is this vertical distance right here between the y point and the line itself. Notice it's not the orthogonal distance, right? It's not orthogonal, so that's a right angle. It's the vertical distance, right? It's the y minus what the line through the origin would predict given that particular xi value. So again, this is exactly the origin as a pivot point, picking the line that minimizes the sum of the squared vertical distances of the points of the line. And we can use RStudio's manipulate function again to experiment. And as a minor kind of technical point, well, not even a minor point, kind of an interesting point, we don't necessarily want the line to go through the origin. You wind up with kind of silly results, right? No one is 0 inches tall, so that the data isn't anywhere near 0. So we don't want pivoting it through that point 0, 0 doesn't make any sense. If we subtract the means of the parents' heights and the children's heights, and instead of analyzing the raw height data but the mean centered height data, then the origin of the scatter plot is exactly the mean of y and the mean of x. And in that case, then it's useful to fit it through the origin, because then we're fitting a line through the origin where the origin has meaning. We want to make sure it goes through the average of the data. Okay, so once again, let's actually use the manipulate function in RStudio to investigate what we're doing. Okay, so here we go. I give the code in the lecture notes, but then also you can of course get it from the Markdown document. So here's the idea. Here's our beta, which is our slope of our regression line, and it gives the mean squared error, which is the sum of the average squared distance, vertical distance between the points and the line. And of course, because these circles are bigger, right, that means that they're getting multiplied. There's more points that look like that point, so that they're factoring more into the sum. Basically, the sum is that point multiplied by the number of times that specific XY combination occurs. Okay, and so what the least squares criteria is doing is it's changing this angle, and because we centered it, because it's a regression to the origin, and because we centered it at the average value, here we are, the point always has to go through this middle point right here, which is y bar, x bar, child height, parent height, and it's trying to find the best line. And you can see how the mean squared error changes, right, as the slope of the line changes. Okay, so here's the code that I used, and I just wanted to note, just because I probably didn't have the values set terribly well when I just did it. The slider, this changes the collection of slider values that you can look at, which I don't even think I was including the least squares minimizer point. So in the next few lectures, we'll talk about how you actually get the solution in R automatically and why this is the solution. But in R, the program for fitting least squares regression is LM, and here I'm just subtracting off the mean for the child. Here I'm subtracting off the mean for the parent, and -1 just means don't fit an intercept. R automatically fits an intercept. So -1 says don't fit an intercept. Data equal Galton is telling it the data set that is, or the data frame that it's working. And then here's what the output looks like. It's generally best to assign your regression fit to a variable. So you want to assign it to say fit equals this, or fit is assigned this LM statement. But we'll talk about that a lot more. But here you see the value that minimizes the least squares criteria. So the 0.46, if we were to plot centered child height and parent's height on the horizontal axis, and we had a pivot point right there in the middle. There's my pivot point. It's a big point now. And for all of the parent and child combinations, we tried to pivot this to find the line through that point that minimizes the sum of the squared vertical distances. Well, the slope of that line, and remember the slope is the only thing we need for it because it's regression through, it's fixed at this point through the origin there, is 0.646. And in the subsequent lectures, we'll talk exactly about how you get these things, what you do to make sure so that you don't have to center the data first, and so on. And eventually we'll even talk about how you can put lots of variables in there, not just parents predicting child heights.